Part 3. Before we get into whether or not non-positive term series converge or diverge, we're going to look at another concept. Power series. A power series is basically a function. It's a function written as a series. And the question then isn't, does the series converge or diverge? The question becomes, for what values of x does the series converge? So let's take a look at some examples. Example A, the sum from n equals 0 to infinity of the variable x to the power of n. Now I'm going to write this just a little bit different. I'm going to index it at n equals 1. I don't have to index it at n equals 1, but I want to show you something here. If I write it from n equals 1, then I can write this x to the power of n minus 1. The reason I did that is it now looks more of the general geometric form, and the general geometric or standard geometric form starts with n equals 1. Again, not necessary, but just making it standard. So let's take a look at what this series looks like by writing out some of the terms. Well, the first term of the series would be 1. The next term of the series would simply be x. The next one, x to the power of 2. The next one, x to the power of 3, plus dot dot dot. Now this would continue, x to the power of n, plus dot dot dot. So this is a series because the terms are separated with a plus, and it goes on infinite, so it's an infinite series. Now if I call this series f of x, well, then we have a power series, and the function will look different for different values of x. Now the question becomes, for what values of x will this function converge? Like, for instance, suppose I wrote f of 5. Well, that would be 1 plus 5 squared plus 5 cubed plus so on and so forth, and that would clearly diverge. So what values of x will make it converge? Well, I hope that you can see that this is a geometric series. It's a geometric, and the first term of the series, a1, is equal to 1, and the common ratio is the variable x. So it's going to converge for the absolute value of, we say the absolute value r is less than 1, so here we're going to say the absolute value of x is less than 1. So it's going to converge when the absolute value of x is less than 1. In fact, I know what it's going to converge to. The function is going to converge to 1 over 1 minus common ratio. So this is the function. Of course, this is the function as long as x is between -1 and 1. We call this here the interval of convergence. Right. So just to make this clear here, this is the function written as a power series. This is the function written for certain values of x. Example B, the sum from 0 to infinity, -1 to the n, x to the n. The -1 to the n is an alternating indicator. I'm going to write this in standard geometric, which means indexed at 1. So then this is going to become -1 to the n minus 1, then x to the n minus 1. In fact, to be completely standard, they write the, who is they, I'm not sure, but the standard is to write the common ratio to the power of n minus 1. So I suppose that's the most standard. Let's take a look at a couple of these terms. 1 is the first term, minus x is the second term, plus x squared minus x to the power of 3 plus dot 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 plus -1 to the n, x to the n, plus dot dot dot. So that's the power series, and we want to know for what values of x the power series converges, and really what the function looks like on that interval of convergence. So this is geometric again. The first term, a1, is 1. The common ratio is negative x, and it's going to converge for the absolute value of negative x less than 1, which also yields that same interval of convergence. Now, what does it converge to? It converges to s, which is 1 over 1 minus negative x, or simply 1 over 1 plus x. So this is what the function looks like on this interval of convergence. And the function looks like this as a power series. And I've been calling these A, B. In the notes, it looks like I've written 1, 2, etc. Example 3, sum 0 to infinity 3 times quantity x minus 1 over 2 to the power of n. I'm going to write this standard geometric, 1 to infinity 3 times x minus 1 over 2 to the power of n minus 1. So you can see that this is always the first term, and then this quantity here raised to the power of n minus 1 is always the common ratio, if in fact it is geometric. Okay, so let's take a look at some of the terms. We have 3 plus 3 times x minus 1 over 2 plus 3 times x minus 1 over 2 squared plus dot dot dot. That is our function, and this is geometric. The first term, a1, is equal to 3. The common ratio is the entire thing raised to the n minus 1. So x minus 1 over 2 is our common ratio. And it's going to converge for the absolute value of x minus 1 over 2 is less than 1. So let's just do the quick algebra on that. So x minus 1 is less than 2. So that's negative 2 less than x minus 1 is less than 2. Of course, you know all of this. So negative 1 is less than x is less than 3. So this here becomes our interval of convergence. These are the values of x for which this power series will converge. Now, what does it converge to? What does the function look like simplified? We would say s, or we can say f of x equals first term 3 over 1 minus common ratio. I'd also like to introduce the terminology center of the interval. If you look at this interval here, the center of it is x equals 1. I can also determine that here when I have the absolute value less than 2, I can tell that the center is going to be 1. That's what makes this interior equal to 0. In the other examples, the center was 0, but here the center, x equals negative 1, and this here is the interval of convergence. Example 4. Now, in these examples, they're all geometric. What makes this a little bit different is you have to be real careful about what the common ratio is. I'll index it at 1 like I've been doing, and the common ratio means that everything is raised to the n, or everything is raised to, in this case, n minus 1. So that would be x plus 1 squared over 9. First couple terms. First term would be 1. The second term would be x plus 1 squared over 9. The next term would be x plus 1 to the power of 4 all over 81 plus dot dot dot. That's the power series. I could say that's the power series. I can say that's the power series. I can say this is the power series. And I want to know for what values of x will this power series converge. And any of the other values of x, it will diverge, of course. So this is geometric. where a1 is equal to 1. Common ratio, x plus 1 squared over 9. And it converges for the absolute value of x plus 1 squared over 9 is less than 1. We'll do the algebra. So the absolute value of x plus 1 squared is less than 9. This quantity, because it's squared, is already positive. So I can say x plus 1 squared is less than 9. Now if I take the square root of both sides, it gives me absolute value of x plus 1 is less than 3. And that gives me negative 3 is less than x plus 1 is less than positive 3. Subtracting 1 from each side, negative 4 is less than x is less than 2. So this is the interval of convergence. These are the values of x for which the power series converges. The center of this interval is x equals negative 1. Again, we can determine that from here also. What value of x makes that go to 0? Okay, now what does this converge to? This function over here will converge to, so it's going to equal first term over 1 minus common ratio. Notice I'm not simplifying this. There's no real need to do that. Okay, home stretch. Last part of the lesson 2. This is B. It's the last page of the notes packet. Looks like I got some of my numbering down wrong. So it says example 4. We already did example 4, but this is the new example 4. So in this example, f of x equals 1 over 1 minus 2x. So that's a function, just like any other case. We have this rational function. Now, the directions want us to write this function as a power series. So what we're going to do is recognize this, and not all functions have this property, but this one has the property written as some first term over 1 minus some common ratio. So we can treat this like it's geometric and say, hey, well, this is a geometric sum where a1 is equal to 1 and the common ratio is equal to 2x. So this function then, written as a power series, well, we can write the first term as 1 plus 2x plus 2x squared plus dot 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 plus 2x to the power of n plus dot dot dot. If we wanted to use summation notation to summarize, we can say from 1 to infinity of 2x to the power of n minus 1. We could also use the 0 index, which sometimes just makes it a little more clean, and we could say here 2 to the n, x to the n. That would probably be the cleanest way to write it, and that is true. So when I say that, this equality is true only for certain values of x. It's going to be true when the absolute value of 2x is less than 1, or when x is between negative 1/2 and 1/2. Interval of convergence, the center, x equals 0. More on the center later, but just trying to introduce that terminology now. And we were successful when we did this portion to write the function as a power series. Last example, f of x equals 5 over 1 plus 3x. The directions want us to write that as a power series. So I recognize the special form. First term over 1 minus the common ratio. So perhaps this behooves me to write it as 5 over 1 minus a negative 3x. There we go. And so the first term would be 5 of the geometric sum, and the common ratio would be negative 3x. So I can continue to write some terms of the series, which is going to be 5. Then it's going to be minus 5 times 3x. Then it's going to be plus 5 times 9x squared. Then it's going to be minus 5 times 27x to the power of 3 plus dot dot dot. There we go. I was successful. Now that's not always true. That is not always true. It's only true for certain values of x, and that's going to be true on some interval of convergence. So this is going to be between negative 1/3 and 1/3. No equals here. If it equaled 1/3, well, then it would be a divergent series. So let's summarize now. There are several ways to summarize. I could pull out a 5, and then I go from 1 to infinity. Now, I like to have that alternating indicator, so I'll do negative 1. Think about what power will go there. Then I'll have 3x is the common ratio. Well, it's part of the common ratio. I've separated these two. One is the alternating indicator and one is the magnitude ratio. And the power of each one of these, n minus 1, n minus 1. That's one way to do it. We can also write it a little more cleanly. 0 to infinity, negative 1 to the n, 3x to the n. These are not the only way to do it. You certainly could have combined these together, negative 3x to the n minus 1. That would have been a good indication of the common ratio. That's okay to do. I do like having the alternating indicator out in front, because not every power series is geometric, and this will have some special properties, as you will see in later lessons.